On Wednesday, we didn't quite finish what we were doing before the bell rang. Since I'm going to be gone on Thursday and Friday, this is Thursday, and I want to pick up from where we left off. I thought this would be the best way to do it, since this is new to everybody. And so we started talking about the idea of what's called a rate law. And a rate law depends upon the initial concentration and the initial rate. And so if you have your books, you go get them right quick if you don't have them. And we were on page 561. Page 561. So on page 561, you have a table, 12.4. It has the same as what you see right here. It has the concentration of NH4 plus and the initial concentration of NO2 minus. It also has the initial rate. That's at the very beginning of the reaction, the slope that you would see, for example, on a page in your book, if you want to look at it again. And that would be on page 554. So it's initial rates. And these are 3 different experiments. Remember, the rate law can only be determined by through experimentation and getting the data. So we initially started taking a look at experiment 1 and 2. When you look at experiment 1 and 2, what stays constant in those 2 experiments is the concentration of ammonium ions. And in both experiments, the initial concentration is 0.1 molarity. The difference is experiment 2 has double the concentration compared to experiment 1 when it comes to nitrogen or NO2 or nitrites. So if you can see, when we compare the experiment 1 and experiment 2 of NO2 minus, when we double that, what's happening is the difference in the concentration is double, and you can get that by taking 0.010 molar of the first experiment. I guess that's the second experiment. And dividing it by the first experiment. And you get a value that's 2. And that would be twice as great. So the concentrations is twice as great in experiment 2 versus experiment 1. So we want to look at what happened to the rate change. So the rate change goes from 1.35 to 2.7. So if we look at rates of experiment 1, or I guess experiment 2, versus the rate of experiment 1, the difference is also 2. When we would take 2.7 times 10 to the minus 7 divided by 1.35 times 10 to the minus 7. And what we're going to get out of that is also 2. So that's called a direct relationship. When 1 doubles and the rate doubles, concentration doubles, rate doubles, that is an order of 1. Okay? Now remember, the scenario I told you about yesterday, if there was no change in the rate, and that's not here, we don't have an example of that here, but if there's no change in the rate, that would be considered an order of 0. Okay? So we know the order of NO2 is going to be a 2. All right? And On the next page, we'll talk about that here in a second, how you plug that into the rate law. Between experiment 2 and experiment 3, we have a situation where we have a similar characteristic happening. And that characteristic, when we take a look at it, is looking at the NO2 remains constant in this experiment. And excuse me, and the concentration of NH4 doubles. So what we can do, we can change this experiment 3. I'm just going to go ahead and erase this. So this would be looking at experimentation experiments 2 and 3. So let me erase these real quick. So if we look at NH4 in experiment 3, it is 0.20 molarity. And then we look at experiment 2, NH4 is 0.10 molarity. Again, we get a difference, a rate, or change in concentration that's 2 times the amount. Okay, so that's right here. It's 0.1 to 0.2. If we look at the rate, we're going to put in 5.4 for experiment 3. And experiment 2, we're going to put 2.7. And again, we come out with 2. So again, that's an order of 1. Okay, that would be considered an order of 1. So how would we write our rate law? Okay. We would write our rate law like this. We'd say the rate. Okay. So we have the rates on those 3 experiments. They're given to us as values. That would be 1.35 to the minus 7th molarity per second. For experiment 1, experiment 2 would be 2.7 times 10 to the minus 7th molarity per second. And then the last experiment is 5.4 times 10 to the minus 7th molarity times per second. That is the rate. Okay? So the rate of this experiment equals K, which we could calculate later. We're going to do that. And then what we're going to do is put in brackets our 2 different reactants. Okay? And we had a reactant of NH4 to the N value, and then we also have NO2 minus to the N value. And those will be multiplied one another if we have 2 reactants. So we're going to plug in our orders in this experiment, and it's going to look like this. Rate is equal to K, which we can find later. It's going to equal the concentration of NH4 plus to an order of 1. So if it's an order of 1, we're not going to write a 1 above. We're not going to write a 1 like that. We're just going to leave it like it's written right there. And then what we're going to do is multiply it by NO2 to the minus. And again, we're not going to write, if we squared it, or it'd be an order of 2, then we'd put a 2 up there, superscript. But since it's an order of 1, it's just those concentrations. Okay, what we're going to do is I'm going to have you find the constant using experiment 3. Okay? So this is what you're going to do. You're going to do the calculation. going to give you time to do that. And then I will share with you the information. Okay? So what you're going to do is put in the rate for experiment 3. And the rate was 5.4 times 10 to the minus 7 moles per liter times second. We'll kind of want to write it like moles per liter instead of a capital M there. Okay? That's going to equal, okay, your K times the ammonium's concentration at experiment 3, and that's 0.2 molar, times NO2 minus, which is going to be 0.01 molar. So what we're going to do is we're going to calculate K. All right? So of course we know to isolate K, we divide both sides by those concentrations. And we're going to make sure that we're going to write these units correctly. So on this next page, I'll go ahead and write that again. And set it up to solve for K. So K is going to equal the rate, which is 5.4 times 10 to the minus 7 moles per liter times seconds, divided by the ammonium concentration, which is 0.2 moles per liter, times 0.01 mole per liter. But we won't put seconds in there because it's not a rate, it's just a molarity. Okay? So when we calculate K, go ahead and you guys go ahead and calculate K. What you get is a value that's 2.7 times 10 to the minus fourth. So what are your units? Well, it's pretty important for us to get the units right. And what we'll do, since on the top we have moles per liter, we can cancel that out, and that can cancel out one of our moles per liter. So then what we're left with is going to be the following. When we take seconds divided by moles per liter, it ends up to be liters per mole times seconds. That would be our units for that constant. So that's the rate constant for that experiment. Okay? Now the constants for all three experiments will be the same. If we would plug in the rates with a different experiments, we'd come up with the same K value each time. Okay? So if we would do this again real quick, and we do it with experiment 1, we'd come up with the same answer. And the same units, of course. So experiment 1, the rate was 1.35 times 10 to the minus 7, divided by its two rates, which is 0.10 divided by 0.1 and 0.05. And we come up with the same constant. Okay? It'd be the same constant. Okay? So, that would be one example when you're comparing, looking at orders. Go ahead and turn over to page 362. Okay? Go ahead and turn over to 362. We can look at another example. All right? So we're going to go ahead and do this one here. All we're going to do, we're not going to plug in the numbers or anything to find the rates, but let's look at experiment 1 and 2. BrO3 is doubling. Okay, we're going to try this. When you take a look at, there's 3 different reactants. Okay, you want to come up with the rate law. So what I want you to do is I want you to look at experiment 1 and 2. And then what I want you to do is look at the rate versus the concentration of BrO3. BrO3 doubles. Okay? And then, so, if you take 1.6 to the minus third divided by 8 to the minus fourth, guess what you get? You get doubles. So, BrO3 is an order of 1. Okay? We got another one of those. Hopefully we get something a little different here. Okay? If you look at Br minus, you want to look at experiments 2 and 3 because the other two, H plus and BrO3, they're constant. So when we look at Br minus, this doubles. And if you take 3.2 to the minus third divided by 1.6 to the minus third, this one doubles. So then we know BrO is an order of 1 also. Okay, let's look at the last experiment. Maybe we don't have to look at the last experiment. We want to look at how H plus changes. Okay? So H plus changes, you got to look at experiment 2 and experiment 4. Because when you look at experiment 2 and experiment 4, again, if you look at experiment 2 and 4, then what you see that BrO3 and Br are not changing, but H plus is doubling. So guess what? We get another order of 1. Those are all orders of 1. So there'll be, the substitute will give you some problems to take a look at. And then I'll have you do those, and then we'll look at those on Monday. And then Friday, what you'll do is you'll work on your lab report dealing with Beer's Law.